Okay. Derivative of e to the x is really easy. I know. Now we're going to do exponential logarithmic functions. It's not scary. Okay, it looks scary, but it's not.
Wait, this is like real. Oh my god, was that the last lesson?
Okay. Derivative of e to the x is just e to the x. Okay? So, then if we have something that involves the chain rule, so think of the derivative of the outside, keep the inside the same. When we think of the inside part, think of the exponent is the inside. So for example, if I want to do the derivative of e to the x squared, it would be e to the x squared times 2x. So you just multiply by whatever the derivative of the exponent would be. Okay. So find the derivative of e to the 3x. So that would be, so we'll call y prime, e to the 3x times 3.
So you just write 3e to the x?
Yep. And if you want, you can just do this all in one step, right? It's pretty easy to do the derivative of the exponent. So what would the derivative of the exponent be?
3.
Well, what? It would be
2x plus 1.
Yeah, so this would be e to the x plus x squared times 2x plus 1 or 1 plus 2x. It doesn't really matter. Just make sure you put it in parentheses regardless, because that would have to be distributed if you're actually going further in solving anything. Oops. Okay, that was an ugly circle. I can't erase. Okay, it's going to have to work. Okay. How about this? I'm going to rewrite this as e to the negative x. Ooh. So y prime is going to be e to the negative x times negative 1. So negative 1 over e to the x. Okay. All right, with x cubed e to the x, now we have a u times v situation, right? This is a u times v. So derivative of u would be 3x squared times e to the x plus x cubed e to the x. Now, we can leave it like this, but eventually when we are going to do applications of derivatives in the next chapter, we are going to want to factor out what we can. So if we e to the x squared. So I'm okay with answering it like this, but next chapter, we're going to have to start factoring out a GCF, and then that would be 3x. Sorry, 3 plus x is what I meant to say. There we go. Some sections, there's only 2 sections that are really like word problem. Most of the chapter isn't.
Is it more of this chain rule?
Yeah. Yeah. But because it's applications of derivatives, the derivatives involved usually aren't super, super complicated. We just have to apply them to, like, we might have more like velocity acceleration questions, but then there's also some other ways that we can apply it. Yes. Never mind. Okay, derivative of a to the x. So that just means any base other than e. So for example, if it was the derivative of 4 to the x, that would just be 4 to the x times natural log of 4. So if the base is anything other than e, right, we just have to multiply by natural log. Now technically if it was e, we could still times multiply it by natural log of e, but what's natural log of e? 1. So, and then this is just, again, this format here is just in case this is just if we have chain rule required. Do you need an example of that, or we're good? Okay. So here we have again a u times v situation. So I want to find f prime of x. Okay, so 3 to the 2t. So I want to do the derivative of that. So it's going to start off 3 to the 2t times natural log of 3 times 2. Of course, it doesn't matter if you put the times 2 and then the natural log of 3. So again, this involves the base of 3 and applying the chain rule with the times 2.
So if you were to simplify it, would it be 6 to the 2?
No, we'll all keep that separate. We'll just leave, it would be 3 natural log of 3 times 3. Like there's not much we could do to simplify it. And then here, we're going to leave sine of t the way it is. Then we have 3 to the 2t times cosine t. So this will be 2 natural log of 3 sine of t times 3 to the 2t. Of course, order really doesn't matter, but don't combine. You can even put the 3 here. Just don't make this a 6, okay? Because we know order of operations, you have to do the exponent first before we multiply. And whenever there's a variable in the exponent, you can't combine that with another coefficient. Plus 3 to the 2t cosine t. And then, of course, if we were going to go a step further, like I had mentioned with applying this, we would factor out that 3 to the 2t. I would, again, say this step is kind of an optional step. Sometimes if you check your answer in the book, they will automatically put it in factored form because 9 times out of 10 on the AP exam, like a multiple choice question would give you the factored form as their answer. That's why. So I'm fine if you leave it this way for now. It's just next chapter we'll start factoring out. Yes, yeah.
Do you think you could explain this one a little bit? Because I'm confused on what you did.
Okay, so how about if I take it
Just
apart?
the first step, because the rest I know how
Yeah,
to do.
yeah. Let's say, okay, so u is 3 to the 2t. So when I do the derivative, let's look at this rule. So a to the u, so this whole thing stays the same. So 3 to the 2t.
Okay, and then I want to
Then times natural log of the base. Okay. And then du dx, that just means take the derivative of the exponent times 2.
Oh, okay.
Okay?
So it's kind of like a chain rule within
It is a chain rule within the rule.
Okay.
Okay. All right. What point on the graph does the tangent line have a slope of 21? So let's do the derivative. 2 to the t. 2. Good. 2 to the t. Natural log of 2. And we want to see when this has a slope of 21. So this is going to be this is a calculator question. Actually, I guess we could probably isolate this without a calculator. I can always plug it in later. So if we want to isolate t, first thing we should do. Good. This could potentially be on either one because I could still isolate t without picking up the calculator. Yeah. In this case, yeah, like we could do natural log of both sides of this. Which allows us to move the t to the front.
Oh,
yeah, because of the exponent. And then we can just divide everything by natural. Ooh. It is.
Definitely a calculator. Yeah. Sorry. I agree.
Well.
Yes. Give me.
But we're able to isolate the variable without doing anything on the calculator.
But what if it asks for the exact?
Well, this would be exact. Now, if I ask you for approximate, that's where we pick up our calculator. And the approximate, just, for
I'm
fun.
never throwing away this calculator. It's the best investment I've ever made.
It's a good investment. Okay, so that's derivative of exponential functions. Good? All right.
Oh my god, this is the best trick ever.
Oh, the natural log? Yeah. It is kind of fun. The trick is just natural log of, or the derivative of natural log is 1 over x. It's okay. And then this is if you have to do chain rule. So for example, let's say I want you to do the derivative of the natural log of 2x. Bless you. It'll be 1 over 2x. So it's 1 over whatever we're taking the natural log of times the derivative of 2x, which is 2. So it's just 1 over x. Yeah. Okay, so we want the natural log of 10 over x. So this is going to be a chain rule. You know what I would probably do is write this as 10x to the negative 1. Because when we do the chain rule, we can just do the power rule. So derivative, okay, so this is going to be 1 over 10x to the negative 1 times negative 10x to the negative 2. Okay, so again, it's the algebraic steps that get us. Well, let's just put this over 1. What do we notice about the 10s?
X to the 1.
They're going to cancel, and you're just going to get a negative 1. And yeah, what about the variables?
It'd be negative 1.
It'd be negative 1 over x, right?
No.
Negative 1 over x.
Yeah.
Yeah.
Why is it negative 1 over x?
Well, let's just say I had this. Don't worry about the coefficients because that's just a negative 1. But really, what do I have? I have an x to the negative 2 on the top and an x to the negative 1 on the bottom.
Wait, it's easier if you write it properly. Like if you write
Yeah,
x over x.
you could do that too.
Wait, so x with negative 1 on the bottom just is x on top?
No, so it's
Yeah.
think of it as like
You can have x
think of it
over
as negative
X squared.
2
Minus negative
x.
1. So that would be x to the negative 1. Okay. All right. This stumped us a little bit on the quiz when we had a secant squared of x over 2.
Yeah.
Yeah.
I think I got
I had, so my recommendation, anytime we have a function notation where the like this,
I hated this
so rewrite it, okay?
Yeah, I was
Yeah.
stuck on it for 40 minutes.
I know. I was like,
I
you
treated
made me
this
do
secant
this
like
on
a
the first
sign.
one.
I literally like.
I was
stuck
very
it.
generous on the partial credit on that one, but okay.
I said I was like,
All right, so first thing we're going to do is take 2. Everything inside stays the same to the first power. Okay, that's step 1. This is a 3-step chain rule because we have a squared, we have a natural log, and we have a sine. Okay, so now the next step. So now pretend the 2 isn't there.
1 over sine x.
1 over sine x.
Why?
Because the rule for natural log is 1 over whatever we're taking. Okay, last step. Now we've taken care of the squared and the natural log. Derivative of sine is cosine. Okay, so cosine over sine is cotangent. So I can make that a 2 cotangent x times natural log of sine of x. Okay. So we've done the power rule a number of times, including in this section. This is just for, it says arbitrary real powers. So for example, what if we had a square root of 2 or we had a pi? Well, the rule is still going to be the same. It's just not going to look pretty. So if I have y equals x to the square root of 2, I'm still going to move the square root of 2 to the front. X to the square root of 2 minus 1. And we leave it. Because there's nothing else that we can do to simplify this.
Wait,
It's-
why prime?
Thank you. I forgot my little prime. There we go. There, that's like the most important part, right? And remembering it's the prime.
No, but like you have one.
I had y. I just forgot the prime.
Wait, that's a zero.
And that's the answer.
I kind of like the way it looks.
It is kind of pretty. This one's also
Yeah,
pretty.
It feels so sophisticated. Like, what you know about root 2 x to the root 2 minus 1?
Or sine to the pi.
Oh,
I bet no one
that's even
knows how to do
fancier.
How many know what the derivative of sine
Not many.
x to the pi?
I
So it's
know.
going to be
It's just us. Pi sin x.
pi sine
Hey,
x.
You with your calc last year, come
Wait.
on.
This is the exact same one as the one before.
It's the exact same process.
Oh,
However- Don't forget chain rule.
Times
Yeah.
cosine.
Ooh, times cosine.
Oh, yeah. So cosine.
And
Oh, pi
I
cosine.
really, there's not much I can do to simplify this.
Keep it like that.
I leave it like this.
Beautiful. 2 more pages. No, we're done.
Wait, when is our unit test?
Monday.
Monday?
No, Tuesday. No, Monday. Monday.
Yeah,
No,
she
what did
can't.
we review?
Actually, need to expect you because I have a wedding.
Tomorrow.
Out of town.
Tomorrow's the 21st.
For a whole weekend.
You're so random, can't we?
We review Monday, test Tuesday.
Okay.
Isabel!
It's a day difference. It's the same day.
That's
Oh.
huge. If I got to study all weekend on
Well, no, no, have a test the next day.
Guys,
Sophia is hearing all of this right now.
Hey, Sophia.
Hi, Sophia.
Hey.
And Leah.
And Leah. Hi, Leah. Okay.
Wait, is the test on Tuesday?
Yes.
I think that's the plan.
Tuesday, right?
Okay, everyone,
Finish.
you have to keep in mind there were only 4 sections in this chapter. We did 2 sections and then a quiz, and then we have 2 sections and then the
I know, I just
test.
have a god.
It's really not going to be, you're going to be fine.
You can't have one on Monday.
I can post a practice test.
Yesterday.
I might even have it already posted.
Wait,
From
you
last
do.
year.
You do.
Do we have a review?
Even better, the practice test, if you want to take a look at it, it's posted from last year.
We finished the quiz and I saw that you had the.
Yeah, I don't always, sometimes if I import like last year's information, I just have that posted.
Wait, is there a review day for this?
Monday.
Monday.
Oh, so it's Tuesday.
Yeah. Okay.
Yes. Guys.
Logarithmic differentiation. When do we do logarithmic differentiation? This is when we have a variable in the base and the exponent. Okay, so for example, if it was just y equals x to the 10th power,
Seems like it would just be 1.
right? It would be just 10x to the 9th power, right? It would just be the power rule. Or if it was 10 to the x power, then y prime would be 10 to the x times natural log of 10, right? So the problem that we have, okay, so this is just the straightforward power rule.
Oh, because
And this is the rule that we just learned.
Yeah.
This is exponential. But now we have a situation when there's a variable in the base and the exponent. That doesn't mean there isn't a derivative, but we can't use either one of these rules because they're both variable. So what we need to do is we need to get rid of the variable in the exponent. How are we going to do that? We're going to take the natural log of both sides. So step 1. Now you can also do any kind of logarithm. I just, in calculus, just so you know, we almost always just work with natural log.
Why is it ln if it's natural log?
Natural log?
Isn't it like the other name?
Well, n is for the natural. N?
Law of natural. Natural.
Wait, did I miss like you just said it was like a Latin name? It was like logarithmic natural.
Yeah.
But the n still is natural.
These are the logs.
Okay.
These are the logs that you carry, Mom.
Okay, step 2, we're going to use the power rule to move the exponent to the front. So we're going to leave the left side. So we're going to move that x to the front. Okay. Okay, step 3, we're going to use implicit differentiation. So I want to take dx of both sides. So this is going to bring back, I know, bring back memories from 2 days ago.
Last week.
Okay, now the right side is going to be power rule. The left side is where we have our implicit differentiation because it's a d dx of natural log of y. Okay, so natural log is going to be 1 over y dy dx. So remember, it's the derivative of natural log of y times the derivative of y. Now on the right side, I have to look at this as a u times v situation. Right? And the nice thing about the right side, everything is in terms of x. Okay? So derivative of x is 1 times natural log of x plus x times 1 over x.
So isn't that just 1?
That is. Okay, so I have 1 over y dy dx equals natural log of x plus 1.
Times 1.
Okay, so step 4, yes. Step 4 up here, solve for dy dx. So that means I want to just multiply both sides by y. Okay. Now, if you look at the way it was written to begin with, it was written in terms of x, meaning you only had variables with x on the right side. So the last step, I just want to replace y with what y was equal to in the beginning. So what was y originally equal to? So I'm going to just write this as x to the x times natural log of x plus 1. Just because I want to have everything in terms of x on the right side, because that's how it started out. But that last step is easy. You do not need to distribute this at all. Okay, it's not going to really help you. All right, so So let's try another one. We have natural log of y, natural log of x to the sine x. Okay, why do we do that? So that we can move the sine x to the front. What was the next step? Okay, so d dx of both sides. Notice on the left side, it's always going to be the exact same thing. You want to give this one a try? So product rule on the right side. Left side is going to look identical to the one above it. Good? We still need a minute.
Alright. Whoa, okay.
Whoa. Okay.
Oh, I did forgot this.
Okay.
Did you get the same thing? Look, with sine x times 1 over x, there's not much.
Okay.
We don't have to really do anything here. I don't care if you put the natural log first, cosine first.
I just did 1 over x times.
Oh, if you left it like this, that's fine too.
Okay.
Left it like what?
If you left it as like 1 over x times sine x,
Okay.
that's fine.
What if I didn't write dy dx equals?
That's okay.
It's not in.
Did you do equals equals equals?
No.
Sure. Look, on the AP exam, they're not super picky about that kind of stuff.
Like,
I always put my equal sign, but you know,
why, just
I
like,
should.
I just know it.
You know it equals.
Because like when we did like the definition of limit, you always have to write limit, and like
Yes,
I
that's
did
true.
it. I did all my work, and then at the end I wrote all the limits in because it like messes me up.
Oh, because it's like you're in that
I'm
that
in
thought
the
process.
algebra zone.
You're in the you're in the middle of it, and then you don't
like,
want to
oh,
break that
Yeah.
thinking.
Well, it's
Okay.
like I always don't.
No. Sorry.
Okay.
This case is
So-
convinced that each one of us have like major
So
like
what?
problems.
How do you know?
I sense it.
It's okay.
Like Tammy
Okay, well, I
especially.
mean,
What about
like, is it better than like
Wait, what about
boys?
Oh yeah, me.
See, regardless of boys, it's
Well,
okay.
that's
Yeah, that's a given.
We're
Okay.
fine on the boys.
Okay, if you have your calculator,
I always.
you always have your calculator. Okay.
Wait.
She sleeps with it.
Yeah.
I can assure you she definitely does not. Definitely does not. That is not something.
Wait, is your other calc class like BC? Is it all guys?
And River.
Oh my god,
Could have been in that class.
I feel bad.
Oh.
I'm not.
Yeah, no, it's okay.
It's a time.
What period do you teach them?
F period. But except for today, I don't have them.
Oh,
Oh,
darn.
shucks.
Oh,
So
shucks.
sad, right?
Okay, I'm going to put in here. So I'm going to actually graph this function. 100.
Oh god. Okay. The slipping was made in Korea. If anybody was wondering.
Korea?
This was made in Korea.
I think you're talking about the wait, isn't
I
it?
also thought. Calculator was definitely made in China.
Wait, isn't it E?
It is an E. I accidentally put the 3. There we go. 3 minus.
Well, now you have it in China.
It was made in Asia. Wait, China?
Okay.
Is it in Asia?
You said is Malaysia in China.
I don't know.
It's not
I don't know. We're in calculus class right now. Okay. All right. So this is something we don't spend a lot of time on in this class, but if you take Calc 2 or Calc BC, we do, this is not just an exponential function because exponential functions are great for a short period of time, but, right, if you think about population growth or in this case, what is it, a flu virus or something, there's something called a logistic function, logistic growth. We took
Stop.
AP
Ew.
Environmental Science.
Oh my.
Never say that word again.
Don't.
class.
Well, you wouldn't have if you took it last year.
Okay,
For us.
so basically with the
So it's
logistic
one
growth function is there's a leveling off period. Like it does not just keep going.
Oh yeah,
Right?
what's that called? Scully. What's it called when it just like there's the line?
Oh, max
Carrying capacity. Okay, so we
At
don't.
least I remember.
The one
something.
that was
Class, oh my god.
So we do take care of that in Calc 2. We do a lot more discussion about carrying capacity. We don't do that much in here. It's just all you need to be able to do is graph it on the calculator and then answer a few questions. Okay, so here's the function. P of t is the number of students infected. Okay. T is T days. It says T days. Estimate the initial number of students infected with the flu. So that's talking about P of 0. Now I can do this here, right? That will be here. Or on the calculator. Also, I'm going to change the window. I believe I have a window towards the bottom of the screen. Does it show you what I made my window? Oh, it looks like 0 to 10. And then what did I make my...
109.8.
Okay.
110.
Which makes sense, right? We don't have anything that's going to go below 0. And then I'll make this... Well, I'll leave that.
Negative students had the flu.
I'll make it 110. There we go. So this is that logistic growth function that I was referencing. Okay, it has that. The carrying capacity, just so you know, would be the numerator. Meaning, if there's only 100 students, you can't get more than 100 students sick with the flu, right? That's why we call it the carrying
Like
capacity.
1,000 out of 100.
Exactly. So how do we find, so menu, analyze graph, or no, sorry, we want to do the trace, graph trace, we do 0, 4.74.
Wait,
So we're going to say about 5 students.
Wait, but
You can round up.
How do you have 0.7 of a student?
Okay, so in math, we round to the nearest whole number if we're talking about students. So we
Four
don't.
or more, let it rest.
So
Wait,
how?
4 or less.
Yo, what?
Bro just like yapped and like
4 or less, let it rest.
She thought she ate. Wait, this is like a genuine question. How can you have, if it's saying 4.74, right? You're missing that 0.3
Yes.
of a student.
But it's still more. It's closer to 5 students because again, if you have 100 students and they all come to school, obviously it's not going to be precise. It's not going to be precise. You can't have 3/4 of a person. But you need to. Is it closer to? Let's say it's 4 students and that other student is like almost really sick.
Oh, I thought you were gonna say like almost like.
Almost full.
Okay.
Madeline's like, don't say it.
I thought you were gonna say something that was like not.
Okay. Just round to the nearest whole number, okay?
Okay, fine.
Okay, how fast is
Wait,
the
what about
flu
my
spreading?
comment?
How fast is the flu spreading?
3 days.
We want,
So you want Y to be. Oh no.
okay,
you-
I want to find the rate of change of the virus
50.
at 3. So on your calculators,
Wait,
God.
wait, I feel like you don't need your calculator for this one. Oh, Cammy.
well, okay, so listen.
Cammy.
We are using our calculator. You would have to do the quotient rule with e to the power. It would. You could still do it by
But
hand.
it's e to 0, which is 1.
Oh, you're talking about this one.
No, that one.
Okay, we have to do the derivative at 3. So at 3, I want to know what the slope of this is. Okay, so we're going to press menu. Menu. We're going to go to analyze graph. And at number 5, it gives us a dy dx.
Oh my god.
So number 5. Now it's going to ask you for a position. We want at 3 days, so I'm going to just type in 3. And it gives us 25.
That's the answer?
So how fast is the flu spreading? 25 what?
Per hour.
Yeah, 25
Students per day.
Wait, wouldn't it be per day? But if
Yeah.
it's 3
So
days-
on the 3rd day, 25 students per day are
75
getting
students
sick,
a day.
basically.
Oh, that's lovely.
Lovely, right?
Pretty accurate.
Yeah.
Okay. When will the flu spread at its maximum rate?
So at a
Okay.
slope of
What is this rate? This is the
0.
derivative. Okay, so I'm asking basically for the derivative of this graph. I want to look for I'm looking for the derivative of the derivative. So I'm looking for the rate and I want to see what's the fastest rate. Okay, on your calculators.
Wait, it says graph the derivative of t, but wouldn't it be graph the derivative of the derivative?
Yeah, so do you see how I have an F2 here?
Yeah, so this should help.
So go to F2, press tab. You're going to type in, so d dx you can get, so I'm going to press tab. We can go to the button next to your little book, right? And I can type in, do you see the D?
Oh my god.
So d dx. And I just want to, I don't want to have to retype that, so I'll do F1
Wait, you can do that?
of x. So as soon as you type in F1,
Who was gonna tell
It's
me you
gonna-
could do that?
it's going
No, like thank you for you, but like
Like the shortcut.
So I'm going to show you there's a lot of stuff that we can do on our calculators to check our answers and things like that. So, but it's going to take, so as soon as it goes in bold, then it knows I'm taking that previous function. It'll make it in this lovely red color.
Then you take the max.
So this is the rate of growth of this. So I want to find that maximum.
So like 3 days.
So number 6, I want to find the maximum, number 3. And I want to make sure I select F2. Ah, it's the same. Which makes sense. Look at this.
Because that's when
This
the
is what we
slope is
call
the
a point of
highest.
concavity, a change in concavity,
Yes.
excuse me, a point of inflection, where it's like right in the middle of
It's
that
the
graph.
highest.
So, when will the flu spread at its maximum rate?
25.
When t equals 3 days. What is this rate? We already said it.
25 students per day.
25 students per day.